Okay, so in this video we are going to prove Landen's transformation, which concerns complete elliptic integrals of the first kind, which are defined as follows. And this constant k is called the modulus, and it is strictly between 0 and 1. And Landen's transformation is the following transformation. And this is what we are going to prove in this video. But first of all, let's just change variables in this integral. So if we put x equals sine of phi, we notice that this integral becomes the integral from 0 to pi over 2 of 1 minus k squared sine squared of phi. Alright, so let's start to prove this. So let me erase this. And so we start with this thing over here. So k of 2 times it is equal to this integral right over here, but with k squared replaced by this thing squared. So it's 1 minus 4k times 1 plus k squared sine squared of phi. And now we can simplify things a little. So let me take this thing outside, and it becomes 1 plus k times this integral. So it's 1 plus 2k plus k squared minus 4k sine squared of phi. And let me erase this to make some space. And this thing can be, so I take this k squared, I put it here, and take the 2k I put here, so it's like this. And I can factorize this 2k here to get 1 minus 2 times this. And you will recognize that 1 minus 2 times the square of the sine of phi, this thing is equal to the cosine of 2 phi. So let us replace this. And this whole thing here, it's actually, if you recall that cosine of 2 phi is equal to e to the 2 phi plus e to the minus 2 phi I over 2. If you put this in here, you can factorize this quadratic like this. So it's 1 plus k times e to the 2 phi I times 1 plus k to the e to the minus 2 phi I, because then it's 1 plus 2 times the cosine of 2 phi times k plus k squared. So we replace this in here. And now this is very nice because if we can expand since k, since k is strictly between 0 and 1, and the modulus of this thing here, that thing is purely imaginary, so this modulus is 1. This means that we can expand each of these using the binomial theorem. So we get 1 over 1 plus k to the e to the phi I is equal to 1, so that's equal to 1 plus k to e to the 2 phi I to the minus half, and so it's equal to 1 minus half k times 2 phi I plus, so 1 times 3 times 2 over 4 k squared e to the 4 phi I minus 1 times 3 times 5 over 2, 4, 6 times k cubed to the e to the 6 phi I, and so on. And similarly, you may expand this thing here, and the phi will just have a negative sign in front of it. And the thing here is, if we expand each of these using the binomial theorem, and we multiply out the corresponding series, so each of these is absolutely and uniformly convergent in the phi interval from 0 to pi over 2. So we may expand each of these using the binomial theorem, multiply them out, and we may integrate term by term. The termwise integration is justified because we are integrating a uniformly convergent series over a finite interval of integration. But just things look a bit complicated at the moment, but let's just realize one thing. When we've expanded this using the binomial theorem, and we've expanded that using the binomial theorem, so the expansion of this is just like the expansion of this, just the phi is negative. So the general form of the term we get when we multiply these two series together is of the following form. So I need to erase something to get some space. So it's some constant when I multiply this series by the expansion of this term. It's something like that. So c for some constant c, so if I take e to the 2m phi I times e to the minus 2n phi I, so it's k to the m plus n, okay, when we multiply these two series together, and then we've got to integrate this over this interval. But now we realize something. So we can write this like this exponential more simply like this. So e to the 2m minus n phi I. And now we can see that this integral is going to be 0 unless m is equal to n. Right? Because otherwise, when you integrate from 0 to pi over 2, this integral is just 0. So we can just consider when we multiply these two series, we can just consider when these exponential vanish. So because we are going to integrate it, and those where the exponential does not vanish will just go to 0. So this thing over here, it's equal to, so that thing, it's equal to 1 plus k times the integral of this series. So it's 1 plus half squared times k squared plus 1 times 3 over 2 times 4 squared times k to the 4. We've just squared this term and removed the exponential, and so on. And as we have already seen, we may integrate, that's just, so when you integrate this thing, it's independent of phi. It's just, you just multiply the series by pi over 2. So it's equal to this thing right over here. And recall that thing over here. So what we've shown so far is the following. So far we have shown that 1 plus k times k of 2 of the square root of k, the 1 plus k, is equal to this thing. So we've shown this equality so far. And we wanted to show is this. So what we must now show is the following. That k of the modulus is equal to this. And this can be rather easily done. So here's how we are going to do it. So k of k is equal to the integral from 0 to pi over 2 of this. Right. And we may use the binomial theorem just like we've done to find that this is equal to 1 plus half k squared sine squared phi plus 1 times 3 over 2 times 4 k to the 4 sine to the 4 times phi plus 1 times 3 times 5 times 2 times 4 times 6 times k to the 6 times sine to the 6 of phi, and so on. Right, so we need to show that this thing is equal to this thing, and then we will have proved Landen's transformation. So once again, notice that because k is between 0 and 1, this thing is uniformly convergent over this final interval of phi, and we can integrate termwise. So the termwise integration is justified. So it's the main problem now is to identify the integral of these powers of sines. So we need to, so let me erase this. So we need to find the value of the following. When n is a positive integer. Well, first of all, in the case where n is equal to 1 is easy because the sine, the integral sine squared of phi is just 1 minus cosine of 2 phi over 2, this, and this thing is just equal to half times pi over 2. All right, so what about when n is greater than or equal to 2? So well, there are many ways to evaluate this integral, but we are going to use induction as follows. So suppose that n is greater than or equal to 2, then this integral then you can rewrite it like this. So it's 2n minus 1 of phi times sine of phi. And you can integrate this by parts. And you will get minus sine of 2n minus 1 of phi times the cosine of phi from pi over 2 to 0, and that thing is just 0. But then minus 2n minus 1 times the integral from 0 to pi of minus cosine squared of phi times sine of 2n minus minus 2 of phi. All right, so we need to, so that thing is just 0, so let me erase it. And also let's take this negative outside. So that thing is equal to this thing. And we can rewrite this like that. So, well, let me rewrite this properly. So it's this integral cos squared of phi times sine of 2n minus 2 phi d of phi. And well, we can rewrite cosine of squared like this. So it's 1 minus sine squared of phi. And so this integral is equal to this thing. And then u plus 2n minus 1 times this thing from pi over 2 of sine of 2n of phi d phi, which is exactly this thing over here. So when we bring it here, so we get the following. So let me just, so that's a minus. Let me just bring that here. It becomes like 2n times this is equal to this. And so what we've shown inductively is that the integral of this thing for n greater than or equal to 2 is equal to 2n minus 1 over 2n times this integral. Right, and that's very nice because since we've already shown that when n is equal to 1, then it's equal to half times pi over 2. This means that in general this thing is equal to 1 times 3 all the way, so all the odd numbers up to 2n minus 1 over all the even numbers up to 2n multiplied by pi over 2. That's very nice. And when we replace this in the termwise integration of this, we find that this is equal to pi over 2 plus pi over 2 times half squared k squared plus pi over 2 times 1 times 3 over 2 times 4 squared of k to the 4 plus 1 times 3 times 5 over 2 times 4 times 6 squared of k to the 6, and so on, which is exactly what we had to do, meaning that we have successfully proved Landen's transformation. Alright, and just as a reminder, k is between 0 and 1. And what we are going to do now, we are going to write Landen's transformation in an equivalent format, and we are going to use this equivalent format in the next video to prove a result about arithmetic geometric means and elliptic integral, a very important result in the history of mathematics, first found by Gauss. But so let me state the result. So we want to show that this is equivalent to the following result. Right, so we are going to show that these are essentially just Landen's transformation. So first of all, we see that this whole thing here is less than 1, obviously, because k is between 0 and 1. And incidentally, you will notice that this thing is also less than 1, because it's like a geometric mean of k and 1 over the arithmetic mean of k and 1, and we know that the geometric mean is less than the arithmetic mean. So, okay, let's prove this equivalence. So let's start with assuming that this is true. So if this is true, then k of 2k over 1 plus k would be equal to 1 over 1 plus 1 minus this thing squared. We are assuming that this is true, and we want to prove that this follows. So it's 1 minus 4k over 1 plus k squared, all under a big square root, times, okay, so it's essentially this thing repeated here. Okay, and let's simplify this. So this becomes, so 1 plus k squared minus 4k is 1 minus k squared. So this thing becomes 1 minus k squared, and similarly for all these things. It's 1 minus k squared, and it's and that's under a square root, which we may now take away. Okay, and so this thing is equal to when we rewrite this factor, it's 1 over k over 2. Sorry, 1 plus k over 2. And this thing is, so it's 2k over 2, and that's just k. And actually, sorry, so I've noticed a mistake. So actually we want to show that Landen's transformation is equivalent to this, right? This factor of 2. And now that would mean that in our procedure this half had disappeared. And indeed, if this is true, then this implies Landen's transformation. And now we show the converse. So we assume that Landen's transformation is true, and we want to show that it implies this result. So what we've just shown is this direction. So I put a small tick here, and now we want to show this direction. So okay, so suppose now that Landen's transformation is true. This would mean that this thing right over here, when we put this in here, it's equal to 1 over 1 plus, this thing, 1 minus k squared, 1 plus 1 minus k squared under square root, okay, times k of 2 times the root of this horrible mess over 1 plus this horrible mess. Okay, and now we have to simplify the horrible mess. So this factor is basically 1 plus this thing over 2. So it's over 2. And this thing is like when you put that here and put it inside the square root, the denominator becomes 2. So we just erase all that stuff. And this becomes, so the square root of 1 minus k squared times 1 plus 1 minus k squared. Okay, and that's just 1 minus k squared, which is k squared under square root, it becomes k. Okay, so that's a k. No need for these giant parentheses. Okay. And I have indeed made a mistake, so you will remember that this thing was supposed to go up and that thing down. So actually it's over 2. And indeed now this means that that thing is equal to k of k. So that thing is equal to this, so that thing is equal to k of k. So we've shown both directions. And as we have said, in the next video, we are going to use this form of Landen's transformation to prove a result of Gauss connecting arithmetic geometric means on the one hand and elliptic integrals on the other. So it was a very important result in the history of mathematics.